where will it go? We do not know where it will go. We only know that if you repeat the experiment 1,000,000 times, you get this pattern. But on the 1,000,000+1th attempt, where it'll go, we don't know. We just know that the odds are high when the function is high, or the intensity, and the odds are low when the function is small, and the odds are 0 when the function is 0. So the role of the wave is to determine the probability that the photon will arrive at some point on the screen. And the probability is computed by adding one wave function to another wave function and then squaring. So you got to be very clear. If someone says to you, is the photon a particle or a wave? Make up your mind. What is it? Well, the answer is, it's not going to be a yes or no question. People always ask you, is matter made of particles or waves, electron particles or waves? Well, sometimes the vocabulary we have is not big enough to describe what's really happening. It is what it is. It is the following. It is a particle in the sense that the entire energy is carried in these localized places, unlike a wave. When the wave hits the beach, the energy is over the entire wavefront. This wave here is not a physical wave. It does not carry any energy. And it's not even a property of a beam of photons. It's a property of one photon. Here's what I want you to understand. You send one photon at a time, many, many, many times, and you get this pattern. Each time you throw the die and ask where will the photon land, this function is waiting to tell you the probability it'll land somewhere. So we have to play this game in two ways. It is particles, but its future is determined by a wave. The wave is purely mathematical. You cannot put an instrument that measures the energy due to that wave. It's a construct we use to determine what will happen in this experiment. So we have no trouble predicting this experiment, but we only make statistical predictions. So if someone tells you, I got light from some mercury vapor or something, it's got a certain wavelength, therefore a certain frequency, I'm going to take two slits and I'm going to send the light from the left so weak that at a given time only one photon leaves the source and hits the screen. What will happen? We will say we don't know what it will do. We don't know where it will land. But we tell you if you do it enough times, millions of times, soon a pattern will develop. Namely, if you plot your histogram on where everybody landed, you will get a graph. It's the graph that I can predict. And how do I predict that graph? I say, what was the energy momentum of your photon? If it was P, I will introduce a wave whose momentum is 2 pi h bar over P. Oh, I'm sorry, I forgot to tell you guys one thing. I apologize. I've been writing h bar and h. I should have mentioned it long back. H bar is h over 2 pi. Since the combination occurs so often, people write h bar. So you can write lambda equals 2 pi h bar over P or h over P. Doesn't matter. So I've stopped using h. Most people now in the business use h bar. Because the energy is h bar omega, momentum is h bar k. If you want, you can write this 2 pi h k, and k is 2 pi over lambda. Then you find p is h over lambda. That's how people used to write it in the old days, but now we write it in terms of h bar and k. Anyway, I can make these predictions if I knew the momentum of the photons. Photons have a definite momentum, therefore there's a definite wavelength. I can predict the interference pattern. So where is the photon when it goes from start to finish? We don't know. I'll come back to that question now. But I want to mention to you a historical fact, which is photons were not really found this way by looking at the recoil of a emulsion plate. Just for completeness, I'm going to make a 5-minute digression to tell you how photons are found.